Okay, we're just going to do a real quick overview of heat and thermal energy. We talked about it quite a bit in our energy unit, and so now we're just going to briefly touch on it as we just to kind of go a little bit more into what temperature and heat are. Okay, and so just to get you started, what do you think has a higher temperature? A cup of hot coffee or a warm bath? Well, hopefully you chose the cup of hot coffee, right? Because you would burn yourself putting your finger in it. The bath, on the other hand, probably feel closer to your body temperature. Wouldn't hurt very much. Wouldn't hurt. Probably feel nice in your hand. Okay. The second question, though, which has more thermal energy? Which do you think has more thermal energy? The answer here is the bath, and the reason why is because while the coffee has a higher temperature, the measure of thermal energy, well, temperature is the measure of thermal energy, but it's very concentrated, the thermal energy very concentrated in a small amount. In this case with the water, there's a lot of water, and that thermal energy is distributed throughout this water. If you were to take all of this thermal energy in this tub and put it into that coffee, then the coffee would evaporate instantly because there's so much more thermal energy here in this tub than there is in the coffee. So initially they thought heat was like a thing, like a fluid, and they called it caloric, and it pushed away from itself and flowed outward. And so this is how what they believed that heat was. And today we know that's not true. Okay, we know that heat is the transfer of thermal energy. Okay, so things that have thermal energy want to transfer that thermal energy to other things. Okay, and so this energy, this thermal energy, is basically just a measurement of the kinetic energy of the particles in a system. Okay, and temperature is how we measure that energy. So if you can imagine that if you zoom in really, really close to an object and look at the molecules, an object that's hotter, those molecules are moving around faster. An object that is cooler, they're moving around more slowly. Okay, and temperature is just a measurement of how fast those particles are moving around. Okay, heat, on the other hand, you can see this is this slide needs some updating, but heat is the transfer of that thermal energy from a warmer to a colder object. So, for example, you go outside and you feel cold because the temperature, the thermal energy in your body transfers out into the atmosphere through your skin. You can't do anything about it. It just happens. You can put on warm clothing, which prevents it from happening as fast, but this is what we call a spontaneous process, which means that it's going to happen no matter what you do. You have no control over it. It's something that just happens, and we'll talk about what it means to just happen in a minute. Okay, and so we actually have three different ways that heat can transfer. So if you touch something really hot, like if you let's say you were cooking something on the stove and you forgot it was hot and you touched it, you'd burn yourself because of all the thermal energy contained in it that would be transferred very quickly to your hand. And so that heat transfer is the thermal energy moving from the pot on the oven into your hand, and that's what's going to burn you there. We can also transfer energy through convection, and so this is where wind comes from. When we have areas with different temperatures, the air pushes from one area to another. You also have probably experienced this, if you were, so like there's a great example down here. If you were at a fire warming your hands over the fire, if you hold your hands above the fire, you can feel the heat rising because the warm air is traveling upward. And finally, the last way to transfer energy is through heat, through electromagnetic waves. Okay, And what happens is that heat is when an object has temperature, any temperature, it gives off light. And the energy of that light depends on how hot the object is. And so, for example, a fire is giving off energy in the form of light. You can see the fire burning, and that's energy being lost in the form of heat. Okay. Another way that you can see it is with incandescent bulbs. So the old light bulbs that we used to use that would get really hot, what's happening is they are heating up to the point that they glow, and that light that they're glowing is what we use to see. Okay? And radiation is also how we get heat from the sun, because we're not in direct contact with the sun. Okay? We're not touching the sun, and there's no wind blowing from the sun to the earth. The only way for energy to get from the sun to the earth is through radiation. Now, when heat gets transferred, there are some things that are really good at transferring heat and some things that are not very good at it. And so things that are good at transferring heat we call conductors, okay? Because they allow the transfer of heat through direct contact, okay? And conductors are materials that heat can flow through very easily, and some examples are metals, and the best conductors are things that have free electrons, where electrons can easily travel. Insulators, on the other hand, are poor conductors, and they slow down the transfer of heat. Okay, and so you probably can think of materials that we use because they don't allow heat to transfer very fast. So, for example, a blanket is an insulator, and the example in this image is pointing out the fact that when you use a blanket to get warm, the blanket doesn't provide any heat. All the blanket does is prevent your body's heat from escaping, and so it allows you to warm up by trapping your thermal energy close to your body. And a conductor, so we use aluminum, copper, iron, cookware on our stoves because they conduct heat easily, so they allow food to get hot through they allow the flame or the hot electric grating that it's sitting on to transfer that heat into the food that you're trying to cook. The next thing I'm going to mention is temperature. Okay, so we are pretty used to using the Fahrenheit system to measure temperature. So room temperature about 70 something degrees. A nice day would be 70 to 80 degrees. When it gets up above 80, 90 degrees, it starts to feel pretty warm. As it drops below 70, it starts to feel pretty cool to us. And that's a little bit of just has to do with where we live, because if you live something else, that range of comfortable temperatures might be slightly different depending on what you're used to. Okay, but if you lived in a different country, you wouldn't use Fahrenheit, you'd actually use the Celsius scale. So let's kind of compare those scales. And the reason that we have these scales is because it's useful for us to be able to talk about temperature. And so we've defined the scales in ways that make sense to us. And so for Celsius, the Celsius scale, we say that 0 degrees is where water freezes. Okay, so this is the point of freezing water. Okay, and they said, okay, well, if water is freezing, then 100 is going to be when water boils. Okay, and then everything else in between there is going to be somewhere less than 100 and greater than 0. Okay, and so this is a scale that's completely decided based upon what makes sense for us. Okay, we like to count by hundreds, by tens, because we have a decimal system, and 0 and 100 are reference points that seem relevant to us. Okay, the Fahrenheit scale, slightly different. For the Fahrenheit scale, freezing is 32 degrees. Okay, and we'll talk about why in a minute. Let me try to spell Fahrenheit correctly first. So, and Fahrenheit, 32 degrees is freezing, and 212 is boiling. Now, in the Fahrenheit system, the reason that freezing is 32 and not 0 is because they set 0 to be the freezing temperature of salt water, and I don't know exactly why, but it has to do with freezing temperature of a certain concentration of salt water. But what's really interesting to me with the Fahrenheit scale is that the boiling temperature for water is 212. Now, these numbers might seem really arbitrary, but what's significant is that the difference between 32 and 212 is 180 degrees Fahrenheit, which is really interesting because when the Fahrenheit scale was defined, they were thinking that, so culturally 180 degrees means to go the opposite way. And so what happens is they were thinking that boiling was the opposite of freezing. And we have a different view of the properties of matter now. We understand that freezing and boiling are not opposites. They're just different points along a continuum. But they said 180 degrees because these are the opposite. And 180 is also useful because it can be divided up into really small pieces. Okay? But so anyway, 100 degrees is the separation for Fahrenheit between freezing and boiling. Okay? So if we want to convert between these, this distance here is what we use. So we say 180 degrees Fahrenheit per 100 degrees Celsius, which simplifies to 9/5. So that's kind of our conversion factor. So let's say if we want to go from Celsius to Fahrenheit, we would take 9/5, multiply it by the number of degrees Celsius, and then we would add 32 to it. Okay, because to get to our freezing point, or to adjust from that 0 point. And then to go the other way, we would just subtract the 32 and then multiply by 5/9. So C is equal to 5/9 times the Fahrenheit temperature minus 32. And this conversion, not super important, but you'll get some practice with it just to kind of get the idea of how to compare those temperatures, get an idea of what means what.